Let's now focus on block floating point format and apply what we learned just now. In block floating point format, you will need to do apply rounding in two different places, and both are critical. So here in this example, I have a hypothetical block format where um, I picked only 5 values, 0 0.3, 0 0.8, 1.2, 2.1, and 7.2. My target block floating point format is MX-EP4, comes from MX1 spec. In MX-EP4, I have two things. I have a scale factor, which is represented in E8M0. I have an element format, which is represented in E2M1. Now, the recipe says that given a block of numbers, you pick the max, which is 7.2. Then you have your target element format, which has a max value of 6. Then you scale it down. When you scale it down, 7.2 becomes 1.2. So that's normalized scale, or the ideal scale. But now we have to consider how do you store this in E8M0 format. When you try to store in E8M0 format, you end up being mapping into one of these legal centroids or legal bucket. And if you look at legal bucket, because it's power of two scales, you only have 1, 2, 4, 8, 16, and so on. And the fraction side, you have 0.5, 0.25, and so on. Now, as you can see, 1.2 cannot be mapped to exactly one of these legal values, so that you have to quantize or you have to round. So here I'm showing here two different rounding formats or rounding scheme, and I'm not telling exactly which one it is. Assume there is a rounding algorithm underneath, but for an example, there are two rounding schemes. In rounding scheme A, it rounds down to 1. In rounding scheme B, it rounds to 2. Right? So the scale, shared scale 1.2, is actually stored either as 1 or 2, depending on the rounding scheme. Now notice that effect of this rounding is on the normalized element value. Because now what you'll do, you'll take the scale and you will scale down all of the values in your input. So 0.3, if you scale it down, here it becomes 0.3 because scale is 1. 0.8 becomes 0.8 and so on. But if you pick a rounding B scheme, then each of the element is scaled down more. So it's 0.15, 0.4, 0.6, and so on. Now that's not the end of it. That's just normalized value in high precision. You now have to think about, or you have to consider, what is the element format? The element format is E to M1, so therefore you have to round down to the element format. In the E to M1 element format, these are the only legal values. I'm just looking at the positive side to simplify this example, but same applies on the negative side. So positive side, you have 0, 0 0.5, 1, 1.5, 2, 3, 4, 6. So now let's say in rounding A, 0.15, if you want to map it, it cannot be mapped. It cannot, we don't have a legal bucket for 0 for 1.5, 0.15. So you have to pick either 0 or 0.5. So in rounding A scheme, you pick 0. In the rounding B scheme, it picks 0.5. Right? So in the rounding A scheme, you make use of 0, 0.5, 1, 3. See, same values repeated twice, meaning that two values got collapsed into one particular centroid. In the rounding bin, this also happens interestingly that both gets collapsed into 0.5, but these are different values. So now if you calculate the total error, you will see that you accumulated different amount of error. Now one thing to notice here is that the element rounding scheme has an effect on the element, but the scale rounding scheme has an effect on scale rounding and also has an effect on the element rounding or the elements itself. So notice that I'm changing the scale rounding scheme. The final values change quite a lot. And that depends on which rounding scheme is picked from each side. So round A and rounding A on both sides has an effect Rounding A and rounding B has an effect. Rounding B on the left and rounding A on the A has an effect. Rounding B on the left and rounding B on the right has an effect. So therefore, in combination, there are quite a few options or results available, and you actually have to try out and figure out for your given distribution what works and what doesn't work.